The next part is going to be collecting the raw data. Now, for this, you just want to concentrate on the raw data and nothing else. So we want a table. And you've got to think, what are we trying to collect? Right, so if we just come to the side for a second, remember the equation we're using when we've multiplied it out is pi root x over g plus pi root L over G equals T. And the bit we're interested in is the first term. So when we did our y equals mx plus c, we plot T against root x, and we get a line. The gradient of that line is, we call it m, and that is pi over root g. What we want to be able to do is calculate g. So if we rearrange that, g is pi squared divided by m, the gradient squared. So what we need is to collect the data to be able to plot this graph and then make that calculation. So we need to collect values of t and x. We're going to calculate root x later so we can plot it. And actually, we're not even going to collect values of t, we're going to collect values of 10t. So our results table needs to contain x. Probably in centimetres. It also needs to contain a uncertainty. So we make it nice and big, plus or minus, and think about what that uncertainty needs to be. So x, plus or minus, and in centimetres. Now, the uncertainty would normally be half the precision. So as we can measure to the nearest millimetre, the uncertainty would be at least 0.05 of a centimetre. You need to convert that if you were doing this in metres. But actually, it's a little bit harder than that, so you might want to increase this slightly. It might actually be plus or minus a couple of millimetres, but again, you need to write that in centimetres, so 0.1, 0.2, something like that. The second thing, while we're on the level of precision, let's say that you recorded an x value of exactly 12 centimetres. You wouldn't just put 12, you'd put 12.0. Equally, if all of your numbers ended up as point zeros, something is clearly going on, you haven't recorded those millimetres at all. So we do expect to see some millimetres in there. But if it's 12, don't write 12, write 12.0. It reflects the fact that you've put it to the nearest millimetre. Okay, we're also then going to record the time for 10 oscillations. So the same thing, we need a plus or minus. I use the quantity 10t, but you could just put 10 oscillations in words if you wanted to. And, of course, the unit is seconds. So for this part, normally we would say, well, the stop clock measures to the nearest 0.1 of a second. So therefore, should this be 0.005 of a second? Probably it should be a little bit larger than that. You've got to think about your reaction time. Don't go too large. Your reaction time is not as bad as, half a second. I would say 0.3 was probably the absolute maximum you should ever get away with. Okay, so given that information, that's not all that we need. We also need repeat readings. So we're going to need 2 more columns, and I will be calling these 10t1, 10t2, and 10t3. And record your numbers running along. Something like that, or whatever the values are, it doesn't really matter. But record them like that, and again, keep the number of decimal places consistent. If something hit exactly 4.1 seconds, you'd record it as 4.10. Each of these needs a plus or minus, and each of them needs a unit. So make sure that you include all of that information in the headings. The final thing you should do with your raw data is number the rows. And actually, you want at least 6 rows because you want at least 6 lengths. Notice how the values for length don't have to go up in constant amounts. They don't have to go up in 5s or 10s. They just have to be different lengths, and you take whatever reading you get. When it plots itself on the graph, it's not going to matter what the scores are. What's the line of best fit that we're interested in.